Where are all those quantum guys? Okay, so let me get started. Yes, there. And, there's one. There they are. So I covered a lot of measure theory yesterday, and then Mike Mislav covered even more domain theory today. So I thought yesterday. So I thought today I should be a little bit light. There's going to be a lot of category theory, and I'm unembarrassed about it. To get myself psyched for the occasion, Samson took me to a concert by a singer called Cat Power. So now I feel empowered to do category theory. So, as I said, I will keep it at a very elementary level, and feel free to stop me and ask me for examples, or say, boring example, show me another one, or anything like that. So the main theme today is what's the probabilistic analog of the simple notion of binary relation. So if you look at things like label transition systems, what do you have? You have a set of states, you have some actions, and associated with every action, you have a transition relation. So if you have probabilistic transition relations, probabilistic transition systems, clearly you ought to replace those ordinary binary relations with probabilistic ones. So that seems like a nice prescription if we only knew what these things were. So the point of today's lecture is to try and explain that, again by analogy with ordinary relations. So I will actually discuss ordinary binary relations, the thing you learned in kindergarten, but I will try and then lead you into monads and algebras to try and show you how ordinary relations emerge from a certain monad. And then we will look at the probabilistic analog of this. So first we have to look at the category of measurable spaces, because the monad that defines ordinary relations comes on set. The monad that defines probabilistic relations will live on the category of measurable spaces. And finally, I will show you the monad, the Lauvier-Giry monad. And I'm afraid that I've got the accent on Giry the wrong way, but doesn't matter. So, so the Lauvier-Giry monad, which is the thing that generates probabilistic relations. And finally, I will apply it to give you formal semantics for Cozen's language with while loops, which I talked about on the first day. Okay. So ordinary binary relations. You have sets and relations connecting them. I'll use letters from the end of the alphabet X, Y, Z to stand for generic sets, and R and S for relations. And now one can think of a relation R going from X to Y, a relation S going from Y to Z. What are these things? Well, R is just a subset of X cross Y. It's a set of ordered pairs of some kind. And same with S, it's a subset of Y cross Z. And they come with a notion of composition. So you compose the relations R and S by essentially saying X is linked to Z by R composed with S, or S composed with R, if I can find something to mediate that composition. So there has to be some Y such that X is related to Y, and that same Y should be related to Z. If that's the case, then X and Z are related by the composite relation. The Y that witnesses the connection is, of course, hidden when you finally talk about the composed relation. Okay, so this is the absolutely ordinary notion of binary relation. This is the kind of thing we'd like to imitate. Now it's easy to see that composition is associative. You don't have to parenthesize it. And it has a very rich algebraic structure. So even though these are simple things with a simple notion of relation, they can be looked at algebraically from many points of view. So they form what's called a Kleene algebra, which is basically an algebraic axiomatization of the notion of regular expressions. So Kleene algebras and relations form an example of a Kleene algebra. They form a compact closed category, which perhaps you know what that is, or perhaps you don't, but it doesn't matter. It's certainly impressive sounding. And importantly, it's the Kleisli category of a particular monad. So I expect people do not know what Kleisli category means, nor what monad means. So it is part of my duty to explain these words, right?
Power set.
Power set? Power set is named after John Power. No, just kidding. So, so compact closed category, I should just say not exactly what the definition is, but what it signifies. So if you have an n-ary relation, you can designate some of those n elements involved in the relationship as inputs and the remainder as output. But it really doesn't matter which ones you designate as input and which ones you call output. You can arbitrarily repartition it without fundamentally changing what the relation is. And this ability to freely move things from input to output is a feature of compact closure. It is in fact exactly the same feature that you see in finite dimensional vector spaces. And you see that as manifesting itself as the ability to form transposes, which is exactly what's happening with relations, or partial transposes. And that ability is what leads to our standard ideas of multilinear algebra. Okay, so relations have all the structure. In fact, it's not an accident that relations look like vector spaces at the categorical level. So just a few propaganda words about category theory. A lot of people think, what the hell does category theory do for me? My daughter says this to me all the time. So if you're looking for category theory to provide you with 7 powerful theorems that will crack big open problems, it doesn't do that. It's more like a guide and a way of looking at certain things. It might suggest certain constructions to look for. Rarely does it actually tell you, just do this and this will happen. Sometimes it does, but rarely does it do that. So it's in that spirit that I will be using categorical language. It's not as if I'm going to pull out some theorem from category theory and immediately some hard combinatorial problem gets solved. Indeed, a famous computer scientist whose name I won't mention puts on his list of 10 items that indicate a proof is likely to be a crackpot. One of the items is uses category theory. So I'm not going to prove any hard combinatorial things. I'm just going to use category theory as a way of suggesting certain constructions. Okay, so having said that propaganda, let's look at relations from a categorical perspective. So one of the interesting things about categories is that you can have the same collection of objects, but with a different notion of morphism, and you'll get some entirely different mathematical universe. So this happens with set. The normal category of sets, the objects are sets, the arrows are ordinary functions, they're composed of course, and they have that's the familiar universe in which people do standard mathematics. But I can take the same collection of objects and I'll say now the arrows are binary relations from x to y, rather than functions from x to y, and I get something that looks entirely different, even though it's the same objects. Composition in this category is the relational composition that I talked about on the last slide, and there is an identity associated with each object. It's just a diagonal relation, which relates every element in X to itself and to nothing else. Okay, so it is a category. Composition is associative. There is an identity. Blah blah blah. It has all the features of a category. As a category, though, it looks entirely different from the category of sets, even though it has exactly the same objects. And this thing can be seen in many other situations as well. As I said, it shares many of the properties of the category of finite dimensional vector spaces: tensor structure, transpose, trace. In fact, 2 traces that you can define on this category associated with different monoidal structures. So in many ways, the category of relations is very much like the category of finite dimensional vector spaces. And indeed, when categorical quantum mechanics was developed at Oxford by Samson Abramsky and Bob Cooker and others, Peter Selinger, not at Oxford. So a lot of emphasis was placed on axiomatizing quantum mechanics just in terms of certain kinds of monoidal categories, and the category of relations was shown as an example of a kind of a non-standard or deviant quantum mechanics that has shared many of the mathematical features, but not all. Yes?
You used the term monoidal category. Can you say, sorry, what?
Right. Treat me as a web page. Anything you don't understand, go click and I will explain it. So, monoidal category. So you have a category equipped, as always, with the notion of morphisms and composition of morphisms, identity morphisms, but now I'm going to equip it with a new gadget called the tensor product. Okay? And what it is a bifunctor. So it will give you, For every pair of objects in C, it will give you a new object, or it will also, for every pair of morphisms, it will give you a new morphism. Okay, so it's exactly the tensor product. So, so in the category of sets and relations, the ordinary product, Cartesian product, is an example of a monoidal structure. Okay, but it's a very special one. It has special features that are not there in all monoidal structures. In the category of finite dimensional vector spaces over some field, the tensor product that you learned in linear algebra or multilinear algebra is a monoidal structure. So there are a bunch of axioms that one has to impose in general, which are very, very generic. But monoidal categories occur all over the place. The feature, or rather the special feature that's present in the case of the Cartesian product, which is not there in generic monoidal structures, is the ability to project onto the two components. So if I form the tensor product of vectors, there is no way necessarily of reconstructing the two vectors from which I constructed my outer product, right? Yes, so there are many, many examples. So for the category of relations, you can take disjoint union as one monoidal product. You can take ordinary Cartesian product of the underlying sets as another monoidal structure. So a particular category can have two monoidal structures. Samson's Hilbert spaces, well actually they're Hilberts, also had a monoidal structure. Okay, so basically it's a fancy word for tensor. Now, any relation like that corresponds uniquely to a function. So if you remember relations, they don't have to relate everything in X to things in Y. So some things in X might be left out, and some things in X might be related to multiple things in Y. So they're completely wild and barbaric compared to the strict discipline one imposes on functions. Nevertheless, there's always an equivalent function that goes from X not to Y, but to the power set of Y. And it's defined in a very simple way. You say f of x is simply the set of all things to which x might be related. And of course that set could be empty, signifying that this relation doesn't have to be defined on every single thing in x. And of course this set could be more than a singleton, signifying that a particular element could be related to multiple things. So you see, even though relations are wild, they have in some natural way an associated function. And in fact, any function like that from x to the power set of y defines a binary relation. Okay? And in fact, if I take any function like this from x to the power set of y, I can lift it with a dagger to a function from the power set of x to the power set of y, where all I'm doing is I'm saying when I apply f dagger to a subset of x, I look at each element in that subset, form the set f of a, and take the union over all of it. Okay, so this is just a direct image. I will write this as just f of a. Okay, so we can go back and forth between thinking of these relations in the way we were taught as sets of ordered pairs, or thinking of them as functions going from x to power set of y. Now, composition of these functions, if you work it out, corresponds exactly to relational composition. So if I take these daggered things and compose them, if I took relations, constructed the associated functions, lifted them in this way, then composed them, and asked, now what does this correspond to? Indeed, it would be just relational composition. So all this is really elementary stuff. So I want to abstract it and make it categorical, which will then serve as a launching point to look at it in a different, not so elementary setting. So we see there's an intimate relation between the category set, the category of relations, and the power set operation. Okay, so this is the correspondence that I'm seeking to generalize. Okay, so let's look at this power set ingredient categorically. So we have this category of sets and functions. We have a functor called the power set, which assigns to each set the collection of all subsets, which is simply another set. And it's functorial, so that means if I have an arrow from x to y, I get an arrow p of f that goes from p of x to p of y, and it does the obvious thing. It takes the image. Okay, but there's extra structure apart from just being a functor. It has the property of being a monad. And since I've not defined what it is, I thought I would actually tell you first through this example what a monad is. Okay, so this has extra structure. For every set, there is a special map that goes from x to the power set of x. And what it does is it takes the element x and embeds it into the power set through the singleton embedding. Okay, so this is a very natural map. All right. There's also a very special and very natural map that says if you give me a set of sets of x, a set of subsets of x, so power set squared of x, there's a natural map that takes me from that to the power set of x. And what is it? You give me a family of sets, well, I can just take the union. Okay? And in fact, this is a general theme in monads. Basically, it says you have two levels of structure. You kind of wipe out one level of the curly brackets, and that will give you a thing one level down. Okay? And this is given by union. Both of these are very natural things to construct. Okay? So, of course, this is a very irritating word. It's like one of those highly overused words in mathematics. Others are regular. And the third highly overused word is normal. So let me explain what natural means in this setting. It actually means something technical. And indeed, it is said, I'm not sure how much I believe it, but it is said that category theory was invented to make precise this concept of naturality. The original paper was indeed called The Theory of Natural Transformations. So there it is. Naturality means the following thing. It means that picture, but I'll come to the picture in a minute. It says, look, you're doing a construction on a whole bunch of different things. And what you want to do is to do this construction in such a way that it doesn't use special internal features of the gadget on which it's being done. Okay, so I'm constructing the power set of x. I shouldn't look inside x and say, I see this particular x has these special features. I will use it in my construction. I should be blind to that. And that blindness is what makes the construction natural. It's not exploiting special features of x. For example, natural constructions in vector spaces should not look at the basis and say, I'll use this basis and do something very basis specific. Rather, it should use something that it should be a construction that says, let me just take the vector space in its most abstract form and do something with it.
So does this have anything to do with the definition from Leibniz about an object without windows?
I'm sorry, I don't know.
Leibniz had a definition of a monad. That's the first time I ever heard of it.
Did he?
Is there some relationship here?
No.
No.
You know about this?
Yes.
So what is Leibniz's definition of monad?
It's just an accident.
Yeah.
He used the word monad?
Yeah, but for something completely different.
Oh my goodness.
Except that I read that it was an object without windows, which sounds something similar to what I
I
just
think
heard.
there's some stuff about Leibniz monads in McLean.
I think McLean, Eilenberg and McLean enjoyed using terminology from philosophers.
Just to confuse people.
Category from Aristotle and functor from Kant, but I don't think it's related. I don't think
This notion is
it's
just,
related to.
it says a play on the word monoid.
Yes. So that's right. So McLean says in his book that he uses monad to resemble the word monoid. So the word monad came into use a bit later. It was first called something silly like standard construction. No. Dual standard construction, which is like a name that doesn't mean anything. Perhaps the fourth most overused word. Then Mike Barr and John Beck started calling them triples. And in fact, I as you know, I work at McGill, and we're forbidden to say monad. At least in the math department, we're forbidden to say monad. We have to say triples. We have to remember to say triples. But outside, when Mike is not watching, I say monad. So let me get back to this naturality concept. How does this capture this idea that I'm not using special features of x? So I have x, and I've done something to it. I've built this new gadget, p of x. And now I'm saying there's this mapping that goes from x to p of x. And what this mapping is should be not specially dependent on particular properties of x. It should be done in a way that's independent. So how do I capture that? I say for any function whatsoever between x and some other set y, I look at the functorial corresponding function here, and I look at the eta there, this should commute. So it shouldn't matter whether I did this thing here and then went there, or whether I first went to y and then did whatever I normally do on y. If I use some special features of x, this would not work, right? Because that would be vitiated by going over to y. Who knows? I have no control over what f might be, right? And it's highly unlikely that it will preserve any special feature of x that I used. Remember, this is quantified over all possible y's and all possible f's that I care to write down. Okay, so that's the thing that forces independence of special features of x on the construction. Okay, so this is the naturality diagram for this particular natural transformation eta. Right? So this can be elevated to a general abstract definition of what it means to have a natural transformation between two functors. Okay, so let me give the general definition of a monad. So it's a category together with an endofunctor and two natural transformations, eta and mu, just mimicking the properties that I had on the previous slide. This one basically says a kind of associativity property. It says basically if I do t cubed and go to t squared and then to t in one of these two different ways, they should cohere. And this one says if I go from t to t of x to t squared of x using the functorial image of the of eta and then apply the operation that takes me from t squared to t, then it shouldn't matter if I went this way or that way, and indeed they should both give me the identity. Okay?
What's I?
Yeah, what is I?
Where's I?
Identity.
The identity.
Beta from I to
Sorry, that's the identity functor, the functor that does nothing, or rather it takes everything to itself. Okay, so it's a functor like this. You have an object x, an object y, of arrow f. It takes it to that.
And the notation t to some power x, what does that mean?
Okay, so t applied to x means the functor applied to the object x. T cubed means I applied t 3 times.
Okay, that's,
So in the power set context, it would be power set of power set of power set.
okay. And t,
So let me tell you what this means in the power set situation. Maybe it will be more perspicuous.
I'm just making sure that the t squared in mu goes mu t squared goes to t. That's the same applied twice. Oh, I see. It's the functor that is t applied to itself.
Yes, but let me tell you what it does for power set.
Okay.
So, so if this was power set, I'm taking sets of sets of sets of x. I have some x. I take sets of sets of sets. And this thing says, first take the union of the inner things. So I have sets of sets. Then take the union of that, and I'll get something. And this thing says, first take the union of the outermost inner brackets. So then I get another set of sets and take the union of that. It shouldn't matter. So it says, in fact, if I have nested curly brackets, and I say, you should wipe them out because that's what union does. So one way of going around that says wipe out these guys first. And you've got this, and then the next one says wipe out these guys, and now you've got a flattened set. Going around the other way says wipe out the outer ones first, and then the inner ones. Amazing how trivial it all is when you give it in a concrete example.
And in the right diagram, the parallel lines in the middle, what do
It
they
means the same.
Oh,
Identity.
oh,
Yeah.
okay.
Right. Thank you. Okay. So that's a generic monad. So I've shown you a monad already. It was kind of the example that drove the definition. Maybe I'll show you another one. So a monad that often arises in doing automata theory. You have a set X. You form the set of all words. So it's actually giving you a monoid, but don't tell anyone. We'll just pretend it's a set. So we view this functor, we call it T, going from set to set. Okay, is this really a monad? Well, let's see. Do I have a way of going from this to that? Well, sure. X star is a set of strings. This is strings of strings. And what do? Concatenate them. You get a string. Do I have a way of doing that? Sure I do. I take a letter and regard it as a string. It's exactly the analog of what I was doing with power sets. Do I have that kind of square law? Well, if I have strings of strings of strings, and I wipe out the levels of structure until it's completely flattened, it doesn't matter in which order I wipe it out. So you see, these things are saying very generic things.
One last question.
Yes?
On the rightmost arrow going down, what is the label of that supposed to be?
That's T of eta of x. I'm sorry. This one, yeah?
Yeah.
It should be T of eta of x.
No, that's mu of x.
Sorry. That's mu of x, yes. That's right. That's T of eta of x. That's mu of x, going from T squared to T.
So that it's the same as it's the same mu as the other.
Yes.
There's a subscript missing
Yeah.
on the left hand side.
Yes. This one should have had a mu of x.
Let's see, mu.
I didn't expect anybody was going to look at this one. Why the hell do people do this? Okay, so this is the categorical way of doing universal algebra. So I don't want to go at length into universal algebra here done categorically, but given a monad, you can construct algebras from a monad. Okay, so how does this work? So if I have a monad, I look at a particular x on which this monad acts, so I get this new object T of x. And I may or may not find an arrow like this. Let's say I do. Such a thing is called an algebra for T. Now, if you look at this monad of strings thing that I did, and you ask, what on earth does algebra for that thing mean? Well, it says, I have a way of doing that. I have a way of going from here to here. And you can see from these equations, it's exactly defining a monoid. So in fact, the category of monoids can be constructed as the category of algebras for that particular monad.
A couple of diagrams.
And there are a couple of diagrams that I'm eliding that have to be added for the category of to be an algebra. But the basic structure you can see emerging. It says, you have to give me a rule that tells me how to convert a sequence of these things into a single thing, and that's basically monoid multiplication. Okay, but this is not the category I wanted to talk about. Given a monad, there are two associated categories that one considers in general. One is the so-called Eilenberg-Moore category, the category of algebras, and it leads to the categorical way of doing universal algebra. There is another one called the Kleisli category. Okay, so as I just said, monads are the main ingredient in the categorical treatment of universal algebra, but I don't want to do that. What I'd like to do is show another closely related construction you can do if you have a monad that yields yet another category. So here's how it works. So you are given a monad T on some category C, and I'm going to define a new category C sub T with the same objects as you have in C, and I think it will be easier for you to follow if I do this on the board rather than have it flash at you on the slides. So the objects of this category are exactly the same as they were before. Okay, so I have objects x and y from my category C. Remember I said you can have the same objects and just change what the notion of morphism is. So I'm going to define a new category by changing the morphisms, not by changing the objects. Okay, so what are the new morphisms? So I'll say a morphism f in CT is a morphism also called f from x to ty in C. Right? So this is called the Kleisli category. But before we get ahead of ourselves, I have to tell you how to compose these things, because arrows have to be composed. Now, in C, we know how to compose things. So let's say I have an arrow from x to y in CT, and a arrow from y to z also in CT. Somehow I have to construct an arrow from x to z, and I'd like to call that G circle F in CT. Okay, so you say, look, these arrows in CT are just actually related arrows in C, and I know how to compose things there. So let's do it. All right, so you go x to ty. So this f from x to y in CT was really an arrow f from x to ty. And then you say g goes from y to tz. And you see these don't match up. Okay, but we do have this functor t sitting around, so we can apply t to everything. Now they do match up. Okay, so I can indeed go like this. Well, that's good. Unfortunately, I was supposed to wind up in tz, not in t squared z. But I have mu that knows how to smash me back down to t. So this gives me a composition rule for the Kleisli category. If you look what happened with the power set, I had a function from x to power set. I looked at its direct image. Then I got too many things. It was sets of things in y, but then I smashed them down. That's exactly taking the direct image. That formula, if you remember, had a union in it. And this mu map is nothing but taking union of a family. Okay, so you can see how the Kleisli category construction is mimicking what I did before with the power set functor. Okay, so this is just describing what I've told you on the board. Okay, so doing this with P is exactly what we did before and gives relational composition. So this tells you how the power set viewed as a monad yields another category called the Kleisli category of that monad, and that Kleisli category is the category of relations. So all this is super fancy abstract way of doing something that you probably knew how to do anyway. But let us follow this path again on less familiar territory. Okay, so we start with measurable spaces. The objects are measurable spaces as I described yesterday, and the arrows are measurable functions. We know that they compose, they form a category. In many ways, this category of measurable spaces is just like set. It isn't exactly like it, but it has many similar features. In fact, it's something called a topological concrete category, so it's complete and co-complete. So, so you have lots of space to do stuff, lots of ability to do constructions in this category. Now, what about adding probability measures to this picture? So you can say, all right, my objects will be not just sets equipped with sigma algebras, but also with probability measures. And I'm going to say the arrows have to be measurable and perhaps also measure preserving. And you can get a category this way. It tends to be rather rigid. It's easy to say what it means to be measure preserving. It basically says the image measure under this measurable function has to match the measure that's already there. So you can define a category like that. It tends to be kind of awkward and things don't work so well in it. There are ways of getting around it, and there are categories one can construct and do certain things with, but it turns out to be much more fruitful to put the probabilities into the arrows and not attach them to the spaces. So that's what I'm going to do.
So, can you maybe it's too elaborate to say, but can you say what does not have products mean?
Right.
If it's too much of a person,
No, my whole purpose is for you to ask questions like that. Okay, so a product says if you have two objects, I can construct a third object that I'll call the product, which has certain special properties. It's equipped with maps like this.
projections.
Yeah, well, yes, they're called the projections in set, but in general, we'll just demand that they're. So how do I say something like projections without talking elements? Dexter Cozen wrote a song called Categories Uber Alles. You can find the words on the internet somewhere. And one of the lines was, we know that elements are just a hack. So we have to try and say these things without talking about elements. So I'd like to be able, so normally we'd say, oh, look, we have set pairs of elements, we grab one or the other, but I somehow have to say that just with arrows. So we'll say, give me a third object Z. And supposing I'm equipped with morphisms like that, then there has to be a unique morphism from Z into X cross Y such that everything commutes. And this is exactly the property that the Cartesian product has in set. To say that this category does not have products means I can't always do this. So this is one of the senses in which I mean category theory guides you. You'll start building up some constructions and you ask, gee, I wonder if I have products. And then you find I do or I don't, and you start thinking perhaps my definition needs to be different. So it's a guide, not an answer. And so now we come to the Lauvier-Giry monad, which is the way we're going to define probabilistic relations, the analog of all the simple things we did before. So the underlying category is MES. We're going to define a functor, an endofunctor gamma, named in honor of Michel Giry, from MES to MES. So this monad was actually discovered by Lauvier and written up in a typescript called the category of probabilistic mappings. And he clearly was aware that it has a monad, he just didn't use this language. So how does it work? It's an endofunctor on MES, so it takes a set equipped with a sigma algebra and it produces this thing, the set of all probability measures defined on that sigma algebra. Okay, so these are set functions. This is just a set. I have to also give it a sigma algebra, right? Because it's supposed to be an endofunctor on MES, not on set. But already you can see, this is some kind of probabilistic analog of the power set. Just like as before I had the set of all sets, now I have the set of all probability measures. I don't like to use the F word, so I will call it a probabilistic analog of power set. Now, gamma x needs to have a sigma algebra structure on it. So how do I do that? For every measurable set, there's a natural function. Perhaps I shouldn't use that word too often. There is a nice function called evaluate at A, defined like so. So what it does is it says, you give me a measure and I will give you a number between 0 and 1. And how do I produce that number? You give me the measure and I'll just evaluate that measure on the set A. Okay, so for every A, there is such a function, evaluate at A. So what I'm going to do is endow my collection, gamma of x, with the smallest sigma algebra, making all of these maps, I'm sorry, this was a typo, it should be EV of A, measurable. Okay, so all these evaluation maps should be made measurable. Now, what do I mean by smallest sigma algebra? So if I make every single set measurable, then every single function in creation will be measurable, because inverse image of measurable sets have to be measurable. So I'd like to be as conservative as possible about deeming sets to be measurable, just enough to make all these functions measurable functions. So you can give a more explicit description, but this is the one that really gives you a feeling for how the sigma algebra structure is put on this. It has to be a functor too, right? So given a measurable function from here to here, what's the arrow part of that functor? Well, it's just composing with the inverse image. And that, of course, will take you from gamma x to gamma y, as it is done here. Now, I claim this thing is actually a monad. So I need to give you a map eta and a map mu, and these should be, as I'm very much trying to mimic the power set, these should be evocative of the singleton embedding and of the union. So what's the singleton embedding? Well, the obvious thing to do, of course, is the Dirac delta distribution. So what it does is it says, I will map every point in X to a suitable measure, the measure whose entire mass is concentrated at that point. Okay? So this was the Dirac measure that I introduced yesterday. So this is just like a probabilistic power set with a singleton embedding. But what is the analog of union? So that's not so clear. So what do we need from our union? It said it should take distributions over distributions and flatten them out and give you a single distribution. Right? Just like set of sets should be flattened out to a single set, I have to take distributions over distributions and flatten it out to a single distribution. Okay, so let me use capital omega to stand for a generic element of this collection. So it's a measure on gamma x. It's a measure on the space of measures. All right, and when I mu of that has to be a measure on this thing. Right, it has to be an element of gamma x, i.e. a measure on x sigma. Okay, what is a measure on x sigma? It says if you give me a measurable set, I'll give you a number. Okay, so give me an omega, give me a measurable set, I should manufacture a number. What can I possibly do to get this number? Now you recall that these evaluation functions from gamma x to 0, 1 are measurable functions. We set up the sigma algebra on gamma x precisely to make these things measurable functions. All right, so we've got a measurable function, we've got a measure, they're dying to get together. So we say mu x on omega viewed as a measure, right, it's now gotten flattened, so it's a measure on sigma, so it knows how to assign a number to the measurable set A, and how does it do that? It integrates over the space gamma x, this function EV sub A, using that as the integration measure. All right? So this was less obvious. But it is a perfect analogy with the union construction. Now, numerous equations have to be checked. And yesterday I described something that I call the monotone convergence mantra. You can check all those equations very easily on the special case when you're working with just characteristic functions, and then you just invoke the mantra and everything else actually follows quite readily. So the monotone convergence theorem is really powerful for this. So these are going to be the Kleisli category for this monad are going to be my probabilistic relations. So let's look at them more closely. The objects are measurable spaces. A map h from x to y lambda is a measurable function from x to gamma y. Right? That's how my Kleisli category worked. Okay, so what is it? So it says it's a map from x to the space that maps elements of lambda to 0, 1. But I can curry this. I never remember which one is currying and which one is uncurrying, but you know what I mean. And we can rewrite this as a map from x cross lambda to 0, 1. So I'll view this as a 2-argument gadget. The first argument is a point in x. The second argument is a measurable set in y. And it assigns a number. And what the category forces on you is you say that if I fix the set B in lambda and let this point vary, it has to be a measurable function. If I fix the point x and let the set vary, it has to be a measure. So that's the type of this gadget. Okay? And in fact, these are precisely what I called Markov kernels yesterday, also known as regular conditional probability densities. So they're not almost everywhere okay, they're absolutely everywhere okay. All right? So those regular conditional probability densities emerge precisely from the Kleisli category of this Jiri monad. Okay? And they compose in just the way that you expect. So let's compose them. So I have a map from x to y and a map k from y to z, and the composite map should go from x to z. So it should say, give me a point x from x and a measurable subset c of z, and please produce for me a number. Okay, so what is that number? Well, if I fix the set c, I've got this measurable function in y. If I fix this point x, I've got a measure on y. So again, I've got a measurable function on y, a measure on y, I integrate over y. And this is exactly the thing that I get by composing these Markov kernels. And you can see the analogy with relational composition. Integration is playing the role of the existential quantifier to hide the middle witness. And in fact, if you say, oh, these are discrete sets, so that these are just points, let's say finite sets, hey, this is matrix multiplication. So in fact, this is how we compose the transition matrices of Markov chains also, by matrix multiplication. All right? So I will call this category SREL for stochastic relations. Now we can use this, all this machinery to give semantics to Cozen's language. So let me quickly remind you of Cozen's language. It's just a language with ordinary assignment statements. We're not being very specific about what these f's might be, but let's imagine the language is equipped with some primitive functions for doing arithmetic. We have composition of imperative commands in the usual sense, sequential composition, a conditional and an iteration construct with Boolean expressions guarding both these things. There's no probability explicitly in this syntax. As I said on Monday, you can readily add it with no additional difficulty, or you can imagine that what this language is working on are variables that are already got probability distributions associated with them rather than precise values, and you're viewing these things as transforming those distributions. Okay, so there are a fixed set of variables taking values in measurable space, in some measurable space. And we'll assume that these f's are measurable functions, and that these b's define measurable subsets. If you give me some relatively harmless syntax for writing Boolean expressions, that will easily turn out to be the case. So the semantics is basically, I'll show you or sketch two of them for you. One is called the state transformer semantics, and it takes a distribution and transforms it into a new distribution. As the program executes, variables get manipulated and the input distribution gets transformed into an output distribution. So this is the state transformer semantics, and indeed the meaning of a statement will be a Markov kernel, i.e. an SREL morphism. The only subtle part in all this is how to give fixed point semantics to the while loop. Okay, so in order to do that, let me show you a bit of structure. So here is a very tiny variation on Giri's monad. Embarrassingly, if you Google Panangaden monad, you will get this thing, which is really too small a variation to be worthy of a name. But anyway, this is how it works. The only difference is, instead of probability distributions, I'm going to allow sub-probability distributions. So the total mass total probability measure associated with the entire space X may perhaps be less than 1. Okay, so sub-probability distributions. Now, everything else is defined exactly as in gamma. It works the same, the monad maps, etc., the natural transformations. And from now on, I will use SREL to stand for the Kleisli category of this monad pi. Why bother to make this little change? Well, intuitively, in this language with while loops, you might have non-termination. Some of the probability mass might evaporate into the non-terminating loops. So if you're trying to say, I have some distribution over the final output, well, there might not be any output because the thing might never terminate. Okay, so mathematically, you get a new level of structure, which is that the Hom sets, the collection of morphisms between two objects, now have additive structure, or to be precise, partially additive structure. Now you can't add two probability distributions just, brutally, because it might happen that the total probability associated with the whole space is more than 1. even if they're sub-probability distributions. Each of them might say the total space has total probability 3/4, then you'll get 1.5, and you'll have to do physics to fix that. But what you can do is you can say, we will define certain families called summable families. And summable families simply mean are those that we can sum safely. Okay? And a summable family may even be infinite. So you can axiomatize the theory of categories where the Hom sets have been enriched with this partially additive structure, and they're called partially additive categories. So the Hom sets indeed form these so-called partially additive monoids. I don't want to write down all the numerous equations. You can probably guess them better than you would understand them if I flashed them at you. If I said, come up with the right equations, you probably would. So these things are called partially additive monoids. The axioms allow you to do things like rearrange things at will. This is a kind of associativity property. And there is a nice limit property which is pleasant to impose. So if you have a countable family in which every finite subfamily is summable, then the whole family has to be summable. So this is called the limit axiom for a partially additive monoid. And you would like the sums to interact properly with composition. Okay, so you would like composition to distribute over sums in the right way and so forth. Okay, and then there's an axiom called the untying axiom. If you have x going into a countable coproduct of y's, and then you kind of extract the individual pieces, then what you get has to be a summable family. Because after all, the original thing was a well-defined morphism. It can't be that any one of the pieces cannot be added. Okay. So why does this structure matter? So there's a nice theorem proved by Arbeb and Manas, which says if you have a partially additive category like that and a morphism f from x to y, then you can find a morphism f star constructed, as you can see, from this countable sum, which we will call the iterative f. Now this equation might be readable or not, but the following picture will tell you what's happening. So I have a morphism f going like this from x to x plus y. So what this thing says is, well, you can decompose that into a morphism from x to y and another one from x to x. Not a big surprise. But importantly, you can feed this back. And what this formula, the way you can read it is you think of a particle going through this and you say, it has some probability to exit right away, or it goes here, goes through the loop, and then it's faced with the same decision, goes here, goes through the loop. So you can sum all that sum is exactly what is being represented by this sum, the sum of all those possibilities. So you can see this is actually capturing the notion of iteration. What is nice is that you can show quite readily that this has to be a summable family if the f that you started with came from such a thing. Okay, so it says basically this partially additive. So notice if I didn't have these sub-probability distributions, nothing would be additive. Only the singleton families would be additive. The fact that I have sub-probabilities allows me to have this additive structure. That's what allows me to have this iteration. And that's what allows me to give semantics to Cozen's language. So this is equivalent to the semantics that Cozen himself gave, but it's not how he did it. This was done by me quite a bit later. So now we can do the semantics of Cozen's language in terms of these kinds of morphisms. So the assignment statement is this god-awful mess, but if you look at it closely, what is it saying? It's just the Dirac distribution on this assignment. Okay? Everything else basically says the points stay where they were, but this guy gets updated to f of x. Sequential composition is just composition, but this composition is the SREL composition, not function composition. Conditionals, again, you just split B and the measurable sets defined by B into it and its complement and apply S1 or S2 as appropriate. And finally, for the while loop, you look at the two spaces that you get corresponding to the conditional or its complement. you'll get a map H of the appropriate type, and then you can use its iterate to give the semantics of the while loop. So, so that's the power of having this partially additive structure. So the probabilistic relation idea gives you a kind of smooth transition from what we were doing with ordinary transition systems and ordinary relations, and we have now gone into the world of probabilistic transition systems. So tomorrow I will study probabilistic transition systems over continuous spaces in some detail, and we will talk about when two states of such a system behave the same way. We will define a concept called bisimulation, which captures exactly this concept of bisimilarity. And we will prove a theorem that tells you that two systems are bisimilar, or two states are bisimilar exactly when they agree on the formulas of a certain modal logic. So this is exactly the kind of theorem that Van Bentham proved, and later, and I guess independently, Hennessy and Milner proved for ordinary transition systems, but we'll do it in the probabilistic case. Okay, so I will stop here and take questions if anybody has any.
Just very naively, when you go into the syntax of Cosen, when it says if B then, B is a measure of the set, right?
Yeah, well, B is a Boolean expression. It's interpreted as defining a measurable set.
Somehow intuitively this ought to say that while if this has positive measure, right, it has non-negative, but that's not what's happening, right?
No, it's are you in this set or not?
Are you in the set or not?
Yeah, that's what if is supposed to do, right? Do you satisfy this property? So B is defining some measurable set, and it's asking you, are you in this set? If so, do this. If you're not, do that.
And that's the split that you described.
So in this Cosen language, the way you're giving semantics to it, you're viewing these programs in Cosen's language as transformers from probability distributions or measures to measures. But Cosen's constructs themselves don't involve any probabilities.
Right.
Is it easy to augment Cosen's language with actually coin flips
Yes,
inside?
yes, absolutely.
Okay.
Absolutely trivial to do that, yes. And that's why also another reason why you would like additive structure, because you will then take convex sums of these SREL morphisms.
Okay. Because in that sense, if you do that, then you don't even need to start out with distributions on the, I mean, you could have,
that's right.
You start with something.
Yes, well, you start with direct distributions.
Right.
Yep,
Exactly.
yep. So it's very easy to do that. And I believe maybe in his paper he did that. I just didn't bother to do that. I just want to say one more thing. It's possible to give a dual semantics as well. So just as in ordinary programming languages, you have a so-called forward semantics where you say, here is the original state of the program and it evolves as the program executes. You have a so-called weakest precondition semantics where you say, this was true at the end, what must have happened before? Okay, and it's kind of a backward flow. And so this is called the dual semantics. So you can construct a category of probabilistic predicate transformers, the stochastic analog of Dijkstra's predicate transformers. Again, objects are measurable spaces. So now, given a set with a sigma algebra, you can construct a space of bounded measurable functions. You can think of these as the predicates. The random variables are the predicates. These are what you're observing. And a morphism is now a bounded linear map from this space f of x to f of y. Okay? So that's what it is. Why do I feel I have the right to call these things predicate transformers? Because you can actually prove a duality between these two categories. If you look at the category of stochastic relations op, it's exactly this category of stochastic predicate transformers. Okay, so there's a nice stone-type duality between the forward semantics and the dual backward semantics. Okay, so somebody should ask me, what stone-type duality? So I will tell you that some other time informally. Okay, this is now I'm really going to stop. Any more questions? No? Okay, so we should go for the last break.